So as I said, in this video, you are getting classwork credit for watching it, but the questions that have been embedded within this video and Edpuzzle are being graded based on accuracy, so those are going in as a performance assessment score. Okay, so given this table of data here, and given the fact that we know of a number of independence formulas we can use, your first question is, based on this information, is whether or not a person drives to work, which is what this column's data indicates, is whether or not they drive to work independent of being not overweight. So being, well, just not in the overweight category. So is the probability that someone drives to work independent of the probability that somebody is not overweight? So what I'd like you to do is look up those independence formulas, and after this question I will show you them and we'll go through this example, but look up the independence formulas and calculate whether or not you think these two things are independent of one another. So you've got a number of choices here, and I'm just going to write out the formulas that we've discovered. The big one here is that the probability of some event A occurring times the probability of some event B occurring will equal the probability of the intersection of those two events if they are independent of one another. And that leads to the fact that the probability of A given B would also have to be equal to the probability of A. Or the probability of B given A would have to equal the probability of B. You can use any of these three independence formulas to prove this. So if I'm trying to prove, as I am in this case, that that's a bad place to write it, that the probability of driving is independent of the probability of being not overweight, I'm going to write it like this, where overweight is O and not overweight is O prime, as in the complement of that set. I'm going to multiply them, and if they're independent, then this will equal the probability that somebody drives and is not overweight. So let's see if this is true. And hopefully you've added up all the columns, so let's do that now. The drive column would be 11. There are 11 people who drive to work in this particular study. It looks like there are 31 people who walk, 31 people who are overweight, and of the people who are not overweight, there are 69 of them. All right, we've got 47 people who walk to work, and it looks like 42 people who take public transportation. This grand total is 100 people. So we've got our total number of data here. So now we're going to test our hypothesis here. The probability that somebody drives to work is 11 out of 100, or 0.11. The probability that somebody is not overweight is 0.69, 69 out of 100 people. And the probability that somebody drives to work and is not overweight is 0.03. So if this is a true statement, then they are in fact independent of one another. So I'm going to use a calculator and multiply 0.11 by 0.69, and that gives me, to the nearest hundredths place, 0.08. These two things are not equal. So the answer to that first question should have been not independent. Here's question 2. Is the probability that somebody walks to work independent of the probability of someone being overweight? Tell me whether or not the probability of someone walking to work is independent of the probability of someone in this sample being overweight. So we'll test this, I suppose, using one of the second two formulas. All right, so we'll say that if this is true, then the probability that somebody walks, given that they are overweight, has to be the same as the probability that somebody just walks to work in general. And again, you could have used one of the other two formulas here. You'll get the same result that I'm about to get. So the probability that somebody walks, given that they're overweight, is going to be out of the number of people who are overweight. So there are 31 people who are overweight, and of them, 10 of them walk to work. The probability that someone just walks to work in general is 0.47, because that's 47 out of 100. So the question is, what is 10 divided by 31? And that turns out to be 0.32 to the hundredths place. We're going to be going to the hundredths place on all these. they're not equal. All right, so again, the answer here would be not independent. And then finally, I'm going to ask a third question. Is the probability that someone takes public transportation independent of the probability of someone being overweight? So we're looking at the probability of transportation and the probability of overweight. Determine whether or not those two things are independent. So for this question, let's use the third formula, and we'll take the second component and say that the probability that someone is overweight, given that they take public transportation, has to be the same as the probability of someone just being overweight in general. So of the people who ride public transportation, 13 of them are overweight, and the total percentage of overweight people in this survey is 0.31 or 31%. So what is 13 divided by 42? Well, to the hundredths place, that's 0.31. So 0.31 is equal to 0.31. So in this case, those two things are independent of one another. All right, let's use a Venn diagram here and try to do something similar. So if you add up the number of people who are in this particular survey, it's 106 people, something to keep in mind. And what I want to know is the probability of a person renting their apartment, which is what this indicates, all of these people, is that independent of the probability of someone owning a business? Because maybe I want to know if people who rent their own apartment are more likely to own a business or less likely to own a business. There might be a correlation there. So we're trying to figure this out based on this survey that we've got here. And again, I'm asking, is the probability that somebody rents independent of the probability that someone owns a business? Go ahead and determine that. So let's use that first independence formula to try to figure this out. So if this is true, then the probability that somebody rents times the probability that someone owns their own business is going to be equal to the probability that somebody rents and owns their own business. So we'll calculate these probabilities and multiply them. The probability that somebody rents is 69 out of 106 people. Don't forget that these two include all the people who rent. Okay, now the probability that someone owns their own business is going to be 23, similar situation, out of 106. And the intersection is just those 8 people. So let's calculate these values. If I use a calculator and multiply these two fractions, I get approximately 0.14. And if I do 8 divided by 106, I get approximately 0.08. So these two things are not they are not independent of one another, and they are not equal. So we've proven that since these two values are not equal, these two events are not independent, which means they are not operating independently of one another. There is some sort of relationship happening between whether or not you rent your apartment and whether or not you own your own business. All right, this one's a little bit challenging. So the probability of an individual being born male is 0.5. And the probability of a person who is born male majoring in English is 0.04. So let's just write down what we've got here. The probability of being born male, which we'll just write like that, is 0.5. And the probability of a person who is born male majoring in English is 0.04. So being careful how you interpret that. What that's saying is the probability that somebody takes English or majors in English given that they are born male. Right? Because the probability of a person who is born male choosing to major in English, it's difficult to interpret there, but that's what that's saying. Assuming that the events born male and major in English are independent of each other, what is the probability of an individual majoring in English? So I'm just going to give you a hint. This is going to involve a number of the independence formulas and our probability formulas. Work these around starting from the premise that these two events are independent of one another, and then I'm going to run through the solution here. Okay, so first of all, what does this mean? Well, the probability of E given M is the same thing as the probability of E intersection M divided by the probability of M. That's the definition of one of these conditional probability statements. Another thing that we know is that 0.5 is the probability of M. So I could then say that the probability of E and M divided by 0.5 equals 0.04. And from that, I could say that the probability of E and M is equal to, if I multiply by 0.5 on both sides, 0.02. And all I did there was just 0.5, 0.5. All right, so now we know the probability of the intersection. That's another thing that we have. We're assuming that these two events are independent of one another. So let's take the original independence formula, which just says that the probability of M times the probability that somebody just majors in English, regardless of what they were born as, is going to be equal to the probability that somebody was born male and chooses to major in English. We know two of these things now. We know that the probability of being born male is 0.5, and we know that the probability that someone is male and majors in English is 0.02. So now this is just some simple division. All right, divide by 0.5, divide by 0.5. And so that leaves us with the probability that somebody majors in English must be 0.04. So is that a coincidence? No, it is not. I chose to use the original independence formula that multiplies our two probabilities together. But if you were really strategic, you might have chosen a different independence formula, like this one. That would have made your life really easy. Because if you know that that's true, and you do, because we're assuming that the events are independent, then you're done. Okay, that's just an example, sort of tricky. Apologize for the trick there. To get you to realize that the way that you choose your formula could save you a whole lot of time. All right? And that's the final example. So your scores from these questions will go into a participation or a classwork grade for today.